So, yeah. The topic of my PhD thesis is derived analytic geometry, and let me remark from the very beginning that analytics means both complex analytic and non-Archimedean analytic. So, before starting to explain the main results and how one can build such a theory of derived analytic spaces, let me start with some motivations. So there are several kinds of motivation that I can give, but there is one which is currently under exploration with Tony, which comes from non-Archimedean mirror symmetry. So I want to focus on this. So non-Archimedean mirror symmetry. So it's part of a long-term project suggested by Kontsiewicz and Soiberman. Basically, in its easiest version, says that it should be possible to construct mirror varieties, some special mirror varieties in the non-Archimedean setting. Somehow, it should be easier to deal with this problem in the non-Archimedean setting than in the complex analytic one. And to actually do it, so idea. We start with some family over some base, let's say torus, singular torus federation. Which is singular, is a discriminant in B, and outside the discriminant, the federation is smooth. And we want to actually construct a mirror family to X. So what we want to do is localize at, suppose, for example, that delta is just isolated points, and localize.
Yeah. Are these algebraic toy, or is this an SYZ picture?
I would take it algebraic in this moment.
So like a elliptic curve?
Yeah. Localize at point P in delta, and go to work over Laurent series over C. So this can be seen as a non-Archimedean field, and if I have some algebraic variety over it, I can do Berkovich analytification to construct a non-Archimedean torus federation over this non-Archimedean field. And if I actually want to construct a mirror variety, what I want to do, what I need to do is to count, to solve.
So your T is the parameter of
Some.
Your T is parameter of another.
Yeah, so these are complex varieties. If I suppose that delta is just a bit sketchy this first part, just to give an idea. But if I pick a point,
T is the parameter on delta.
yeah, and I can see like this point as a map from here, so I can just.
This is a transversal coordinate to delta
yeah,
inside B.
Yeah, and then I can restrict to the point neighborhood and work over that. So we need to solve some enumerative geometry problem, counting problem in X, and by this typically means counting holomorphic disk or cylinders. And so these are usually difficult to to count because they are open Riemann manifolds or Riemann surfaces. But there is a theorem of Tony, UAU, that says that when X is actually a surface, we can reduce the count of holomorphic cylinders to closed curves. So we are reduced to count, in the special case where X is a surface, we are reduced to count something like a Gromov-Witten invariance. So when X is a surface, we can reduce to counting closed curves. So we are reduced to formulate some version of Gromov-Witten invariance in the non-Archimedean setting. And yeah, so in the non-Archimedean setting, it's a theorem of Tony. There exists a moduli stack, and the n non-Archimedean Deligne-Mumford proper stack. So if we want to mimic what happens in the algebraic setting, we want to construct some virtual fundamental class of this moduli stack. And to do that, we need some derived enhancement of this stack.
When you say non-Archimedean, you mean rigid analytic or Berkovich analytic?
I always mean Berkovich. So yeah, that's a good question. Non-Archimedean, we call Berkovich. And okay, so the first problem, the first goal is establish the existence of a derived enhancement. Of this non-Archimedean stack. So, of course, to establish the existence of such thing, I first need to define what are derived non-Archimedean spaces and stacks. And then we will need some version of Lurie representability theorem to deduce the representability of a derived enhancement out of the representability of this stack. So this is essentially what I'm doing in my thesis. And I'm going to review now.
Can I ask? So the goal is to put a natural derived structure on this guy,
yes,
so that the Euler character of the structure sheaf is finite. I mean,
yeah,
so you are planning to get a virtual class out of it.
Quasi-smooth derived enhancement. Yeah. But that will be more or less a formal consequence of the existence of the derived structure. Because we are planning to construct the derived enhancement of this guy just as in the algebraic setting as a mapping stack. And the proof of quasi-smoothness is rather easy in the algebraic setting. I believe that the same proof will carry over in the analytic.
Or just because it's curves?
Yeah. So
it's amplitude 1 tangent complex.
Mm. So tool needed for that first is derived non-Archimedean stacks, Deligne-Mumford, and second is Lurie representability. So this is the goal, and the first goal that we posed as ourselves, Tony and I, it's not still quite accomplished, but Lurie's representability is proven. So I will overview the theory until this representability theory. That's the goal of this. So So to understand the final definition that we give of the derived analytic space, let me start with a naive guess of what this guy should be. So the theory, will work for both complex analytic and non-Archimedean analytic. So let me a naive guess. So as you know, in the complex analytic situation, complex analytic spaces are just a full subcategory of locally ring spaces. So analytic spaces are just full in locally ring spaces. So a reasonable guess would be to try to work with simplicity ringed spaces. And more precisely, one could try to give the following definition. Which turns out to be wrong. So the derived analytic space is a pair X OX, where so X is a sheaves on some topological space or sheaves on some quasi-étal topos in the sense of Berkovich, and OX is a simplicial sheaf of simplicial rings. All this means up to homotopy and in a suitable infinity categorical sense. And X pi 0 OX is just a usual complex analytic space for Berkovich space. And fourth condition, we will ask that the pi I are coherent. One can actually make sense of this definition and produce an infinity category of derived analytic spaces in this sense. But the category we obtain is not a reasonable category for the reason I'm going to explain. So let me denote D and K, the infinity category associated to these guys. There is a main problem, which is this category is not closed under push-out along the closed immersions. And let me explain why this is a problem. Not closed under push-out along closed immersion. Why this is a problem? Basically because this is one of the first properties that we ask in the condition of Lurie's representability theory. So with this category, this property is not satisfied, so Lurie's representability trivially fails. Even the easy direction fails.
give us an example?
So let me explain, because it's instructive to understand why this is not closed. So let me explain a bit better. And the counterexample will also suggest how to fix the problem. So let me consider X, OX, an analytic space, either complex or non-Euclidean. And let F be a coherent sheaf, ordinary coherent sheaf on X. Then I fix a square zero extension of OX by F. And I can consider this pair. And I ask myself whether this is an analytic space. So this would be always true if this category would be closed under push out of the closed immersion. Because I can always describe this guy as a push out of X OX plus F shifted by 1. I can always choose a morphism here, such that this is a push out. This is a general theorem in derived algebraic geometry. And but this map is a closed immersion because on pi 0 is just the isomorphism. This is a closed immersion as well. So if this property was true, I would get that this guy belongs to derived analytic spaces. And now the point is there is a counterexample of Gabber that shows that I can actually choose F and O in such a way that this is not an analytic space.
Can you, what's the, the way you wrote it, it looks like an ordinary analytic space. What's the derived structure? What's the complex?
No, it's ordinary. It's ordinary guy here, but here, this guy is...
Oh, I see. You're viewing this ordinary analytic space as a push-out of closed immersions for the trivial derived guy.
Tower are square zero extension.
Okay.
Mapping possible tower.
Okay.
Yeah, so there is a counterexample of Gabber. You can find it in his book with Ramiro, Almost Ring Theory, in section 7. So let's try to understand better what's the problem. If I start with the if I start with the square zero extension here, I can see it, essentially it's a restatement of this theorem. Says that I can see 0 F O O X 0. It's just the same thing as an element in X1 OX cotangent complex of OX F. And now the insight is that this cotangent complex here is too big. So Gabber, there exists an analytic cotangent complex such that X1 L OX analytic F classifies analytic square zero extension. So what we want to do is to find a suitable derived framework where the natural cotangent complex is the analytic cotangent complex.
What's the difference between the big one and the
example? So there is a general property which is this guy is always the maximal finite dimensional quotient of the algebraic one. So example, I take the germs of holomorphic function in one point on the affine line. the algebraic cotangent complex of C is very, very big. But the analytic one is just what you expect. This is just C, Z, Z.
But in the definition,
Yeah,
is
in the definition,
is it defined as, you know,
Yeah.
derivations with certain
Yeah.
properties?
Yeah.
Or, okay.
You can define it in that way. And morally is something like if I give a derivation of C, Z with values in M, instead of just asking Leibniz rule, I would like to ask something like for every holomorphic function. When f is a polynomial, this equation follows from Leibniz rule, but if f is like the exponential, no way to get it. And this is really the difference between the analytic cotangent complex and
So it's somehow you want derivations, formal derivations, which
That
are
are
analytically
completely-
representable.
yeah, and yeah, there are actually things like that. And the way to formulate this is to ask that the derivation is somehow continuous with respect to some, for example, Banach algebra structure on this guy and on this guy. So Jacques Louis' insight is that there is also an almost algebraic way of formulating this condition. So, which is the approach I'm using in my thesis, and that with Tony we are using for non-Archimedean insight. Holomorphic rings can be used to get a workable theory. So to understand what these guys are, let me start picking a Banach algebra, complex commutative Banach algebra. So A Banach algebra, commutative, and over C. Then, if I pick an element in A, I can consider the following, and I fix an open subset of C. I can consider the following problem. I have a map from polynomial to A selecting just this element, and I have holomorphic functions on this open subset. I have a natural restriction function, and I can ask myself when I can complete this diagram. So the given of such lifting is what is called that holomorphic functional calculus relative to U. And this problem has solution if and only if, in which case is unique. So this has solution if and only if the spectrum of A, which can be thought as the image of the Gelfand transform of A, is contained in U. So this question makes sense even when A is not Banach, in which case we have to give axiomatically the given of such liftings. And the given of such liftings would be called an axiomatic holomorphic functional calculus. So if you think about that, what it means, it would just mean that I'm giving a functor from the category of open subsets of Cn to set. So giving an axiomatic holomorphic functional calculus is the same on A, is the same as giving a a functor from open in Cn to set such that O commutes with products, and O of C is equal to A. So Jacob's insight is that we can take this as definition and replace it Banach algebras with rings with such functors and construct a theory of derived analytic spaces using these as structure sheets. So I can give a rough definition, which is quite close to the definition used in my PhD thesis and in Jacob's work. So the given of such functor, I will refer to such a functor as an analytic ring. And it would make sense to replace a set with essentially any category with products. So in particular, infinity category with products. In particular, I could take topological spaces. And or any category of sheaves on some topological space. So rough. A derived analytic space is a pair X of X, where so first of all, X is sheaves on some topological space, or is sheaves on some quasi-étal site associated to a Berkovich space. Second, X. Now, if I have OX is an analytic ring in X. Now, if I have an analytic ring, I can of course forget that I have all these lifting properties and just look at the underlying algebra. So I denote the resulting sheaf of simplicial rings by algebra, underlying algebra, and this is a sheaf of simplicial rings, so I can take it's by 0. And I want this pair to be an ordinary complex analytic space or Berkovich space. And the fourth point, I ask pi I OX out to be coherent. Yeah, so the theorem that starts the theory is the following. So, so this is Rudy in the complex case, and me and Tony in the non-Archimedean setting. So first of all, there exists an infinity category of derived K-analytic spaces, whose objects are the one I defined here. Second, the usual category of complex analytic spaces or Berkovich spaces embeds fully faithfully in derived analytic spaces. Third property, derived analytic spaces has fiber products. And fourth point, which is subtle, because it needs a proof, is if XOX is a derived analytic space, then its truncation is a derived analytic space. I mean, this, of course, you would expect, but it requires a proof and it's not an easy.
Before you raise this, can you
Yeah.
explain what's the relation between the analytic ring and this functor from open subsets?
Oh, yes, an example. Yeah, right. So I will describe this embedding. I will give you, so you will understand what is this O.
Okay.
So, thanks for the question. So, example. So let X, OX be an equal complex analytic space or Berkovic space. Then we take X to be sheaves on X, and we define OX from, so I will call this category Tn. I need to give you a functor that goes from Tn to sheaves, and I define it in the following way. So I take U here. I didn't define this in the non-Archimedean setting, but it's more or less clear. It will be something like smooth Berkovic spaces. I could replace this open with all smooth complex manifold. The whole theory would be unchanged. And in the non-Archimedean setting, we actually take smooth Berkovic spaces. Or you can take smooth affinoid, K-affinoid algebras, and the resulting theory would be the same. So let me just reason in the complex analytic case, because I think it's easier to follow. So if I start with an open subset of Cn, I define OX U. So this has to be a sheaf. So I have to evaluate it on an open subset of X, and this will be the Hom set from V to U in analytic spaces. And you see that this trivially commutes with products in U, and it's a sheaf in V because the topology is subcanonical. Moreover, this belongs to set. So we get X tilde, O tilde X, a derived analytic space. So in this case, the pi 0 is just the structure sheaf itself, because this sheaf is taking values in sets. And moreover, the underlying algebra of this guy is just the structure sheaf we started with. Because to take the underlying algebra means to evaluate on C. So here we would be taking a holomorphic function on the open subset to C. So just holomorphic function defined on X. So this is really the sheaf we started with. Is it clear?
Yeah, how does that home depend on X? It's just that V is something over X.
Because V is an open subset of X. I'm defining a sheaf on X.
I'm sorry, is there like sheaves of sets? Or what kind of sheaves?
It's just a sheaf.
Of set.
Of sets,
Sets.
okay. So, I mean, in your definition of analytic ring, what is actually making it sort of analytic?
You mean what does make OX analytic?
Yeah, I mean, suppose I take continuous maps from V to C, or V to U.
Oh, well, yeah, they are holomorphic maps.
I know, suppose I define an analytics ring where I take continuous maps instead of analytic maps. And why isn't that?
Oh, that would be a C0 ring.
But it seems
Like
like
there are many variations on this idea.
this is your definition of an analytic space, I thought.
Yeah.
So why isn't what I said?
So here you would like to replace a holomorphic map with continuous map.
No, in the definition. Go to
In
the
the
next
definition
word.
of an analytic ring, it seems like you can just let
Yeah.
it be.
Here I'm taking the full subcategory of analytic spaces
Yeah.
spanned by the open subset of Cn. So here it's plus holomorphic
Okay.
And you want a sheaf of sets on that.
Yeah. I mean, you can see it in two ways. You can see it as a sheaf on X taking values in functors, product preserving functors to set out of this category. Or you can see it as a product preserving functor out of this category with values in.
I guess I'm sorry, I just don't see why it's imposing any sort of polymorphicity on any.
It's a sheaf on the analytic side.
So why isn't the continuous functions a sheaf?
Well,
on the analytic side?
okay, let me try to give an example to elaborate more on this example. So, in this case, I have OX tilde evaluated in C. It's just the sheaf of global section on X. But I have actually additional structure. For every holomorphic map from C to C, for example, the exponential, I get an induced map.
No, I know that.
Yeah.
I understand that the analytic guides satisfy your condition. What I don't see is why other things don't. Like
I don't get the question, sorry.
He's saying you're defining an analytic ring as a sheaf of sets on the analytic side
Yeah.
of Cn.
Yeah,
Now, take any sheaf of sets.
yeah.
For example, take the continuous functions on any open
Oh, why
set.
I cannot endow it with an analytic ring structure?
Why isn't that an analytic ring according to your definition? It seems to be an analytic ring according to your definition. Your definition is
Well, in this case,
It's not finitely
the
generated.
product,
say that.
the product computed in the category of like C0 manifold, topological manifold. I think it agrees with the product computed in the category of analytic manifold. So you wouldn't see, I mean, according to this definition I gave, it would be an analytic ring. Actually, I'm hiding, for exposition reason, some condition here.
Okay, I guess
So
that's what I was
maybe
asking for. What conditions are you hiding?
Yeah. So I'm hiding this. So the first property is O is product preserving, and the second property is O take commutes with pullbacks. U x x prime e prime, where u to x is an open immersion, and the third condition is saying that O takes covering open cover to epimorphism subtraction.
Okay, I still don't see any homomorphicity requirement. I mean, there's no finiteness or something, or
No.
theoriness,
No.
or
Just all, in the case of complex analytic geometry, just all the open cover.
yeah. So I don't see why continuous functions still don't work.
Wait, you are saying for any commutative Banach algebra you can construct such a functor? Is that what you
No,
said?
not quite.
Any
Because you-
commutative complex Banach algebra defines an analytic ring with respect to this definition.
Okay.
Which defines the analytical ring in your sense,
Yeah.
right?
Okay, so you do have lots of.
Yeah, there
Big
are a
and
lot
small
of them,
continuous
but we are mainly interested in the analytic rings coming out of usual complex analytic manifolds.
Oh, that's all I want.
Okay.
Okay. Fine.
But it's you see, like this third property in the definition of the derived analytic space, it's restricting a lot the class of
Okay.
analytic rings we are looking at.
Sure. Okay.
Yeah, because we are just like we are asking that this is an order in complex analytic
Okay.
space, so it shrinks the category a lot. Okay, so yeah, so this starts the theory, and then we can actually show that the theory we get is reasonable in the sense that we can prove some fundamental theorem. So analytification and Gaga theorem for this kind of object. So let me remind you that if X, so what we want to define now is, I start with the derived schema in the sense of either Toine-Bezzosi or Lurie, and we want to construct an analytification, so some derived complex analytic space or Berkovic space according to that definition. So let me start by recalling the definition of Grothendieck. We start with the schema locally of finite type over C, and the analytification of X is defined by the following universal property. Morphism in the category of analytic spaces from any analytic space to X is the same as morphism in locally ringed spaces from Y to X. So this property, this is easy to formulate in the language we set. So we want for X or X a derived schema over C of finite type, X analytified, which will be such that map in derived analytic spaces from Y or Y to the analytification is the same as map in, let me denote it, E infinity spaces, just simplicity commutative spaces from Y or Y. The underlying algebra I take, and I go to X or Y. And this gadget really exists. It's a very general theorem of Lurie that established the existence of such objects in much greater generality than we need. The problem is that the theorem doesn't really explain how to construct it. So the first problem that we have is that we should try to understand better Lurie's analytification. So there exists such X analytic or X analytic in the complex analytic spaces. And we can summarize the properties of this analytification with the following list. So first of all, Lurie's analytification extends Grothendieck. Okay. Second, very important property is the canonical map from the analytification to the original schema is flat in the derived sense, which I'm going to recall. So it means that on pi 0 is flat, and this is not a big surprise, because thanks to point 1, it's just the usual flatness of the classical analytification. And second property is pi I of the analytic structure sheaf can be computed as the analytification of the pi I of X. So these two points together explain us that to actually construct understand the derived analytification, we just need to understand the analytification of the classical underlying scheme, and then to analytify all the higher homotopy groups. And so the real content of the theorem is, of course, point. And so using this, it's quite easy to deduce Gaga theorems. Let me just give a definition. F from X to Y in derived analytic spaces is proper if the truncation of F is proper in the usual sense of complex analytic spaces. So using this definition, we have the following three theorems. So theorem 1 is Grauer. If F from X to Y is proper, then our F lower star takes bounded below coherent complexes to bounded below coherent complexes. Theorem 2 is Gaga. So if F from X to Y is proper between derived schemes of finite type over C, then the following diagram commutes. So this is an amplification, this is a direct image, and this is an analytic direct image. And plus. And finally, if X is a derived scheme over C proper, then analytification induces an equivalence of infinity categories between the unbounded derived category of coherence and the unbounded derived category of coherence on the analytic space. And so it's worth remarking that we can actually extend all these three theorems to Artin-Stacks. So I didn't define Artin-Stacks. Let me just explain briefly. How much time? No. So let me just put it as a there is a theory of Artin-Stacks, and these three theorems carry over. Yeah, so do you have any questions? Then let me go quickly to the final part, which is analytic deformation theory. So the problem, the most basic problem in analytic deformation theory, to start the theory, is to define a split square zero extension. So, basic problem, I let X or X be a derived but not necessarily K analytic space, and I let F be a coherent sheaf on X. And I ask what is X OX plus the split square direct functions. So I need to define this guy as an analytic ring. So to just give a feeling of what it should be, let me do the discrete case first, and then explain how to define it in general.
F is not homologically shifted, or you don't care?
Let's say that F is in the heart,
Okay.
even in this case. So to understand
But whatever answer you're presumably giving will work for any shift of the heart.
the final construction, yes.
Yeah.
But if I give the final construction immediately, I think it's not easy to get the feeling of what it is. So I can define the analytic structure shift in the following way. So I need to define OX plus F, let's say as a functor from N to set. And basically what I do is I take U, an open subset of Cn, and I send it to OX evaluated on U plus F to the power N. And what I do on morphism, if I give myself a holomorphic map from U to V, then I should construct a map like this. What I do is I take the Jacobian of F as a function from U to matrices from N, M with values in C. If I apply my analytic ring on this map, I get something that goes from O evaluated on U on in matrices N, M, OX evaluated in C. And now I can multiply a matrix here with a vector in Fn. So what I can do is I send A M to, which belongs to OX U plus Fn. I send it to OX F evaluated on A. So the action on the module is somehow by the differential of the function I'm considering. So how to make sense of this in general? The key is the following theorem. So let X be a derived analytic space. Then there exists an equivalence of infinity categories between the category of modules on the underlying algebra and the stabilization of analytic range on X over OX. So this side, you can think of it, if you never saw spectra, you can think of this as abelian group objects. And so this side is, this theorem is quite surprising, in my opinion, because on this side we see some sort of analytic structure. We are seeing analytic rings living over a given analytic ring OX. But this theorem is saying that we can safely forget all the analytic structure to a purely algebraic. And now here we have a forgetful functor from this category to analytic range X over OX. So if I take N here, I send it to N via this equivalence, and omega infinity M is what I call by definition OX plus F. And when F is discrete, it gives me back precisely this construction. So using this theorem, we have a split square extension, and therefore we have also analytic derivation. So let me just conclude with a theorem. the functor, so let X be a derived analytic space. Then the functor which goes from OX modules to spaces, sending M to sections of the canonical projection. Is representable by an object that I call the analytic cotangent complex of X. Second, the analytic cotangent complex satisfies the usual formal properties, by which I mean it satisfies the transitivity sequence and it satisfies the base change property. And furthermore, the analytic cotangent complex is always coherent and in negative degrees. If X is a derived scheme of finite type over X, then I can construct the algebraic cotangent complex of X and analytify it. And this is the same as the analytic cotangent complex of X analytified. So combining this property and the transitivity sequence, we are close to be able to compute, in principle, analytic cotangent complex of whatever. What is missing is the behavior of the analytic cotangent complex on closed immersions, which is given by this property. So if f from X to Y is closed immersion, then we have the analytic cotangent complex of X over Y, and this is the same as the algebraic cotangent complex. Like I forget the analytic structure, I just see them as infinity simplicity ringed spaces. And I computed the cotangent complex in the algebraic way. I get the same thing. So since every complex analytic space can be locally embedded by a closed immersion in something smooth, so in particular in some affine space, the affine space is the analytification of the algebraic one. So combining this property, this one, and the fiber sequence, we are able to actually compute in principle the analytic cotangent complex of an arbitrary matrix. And yeah, so let me just say by words orally, this theorem on analytic cotangent complex has a consequence the fact that this category is closed under push out along the closed immersions. And then this is the first type of Lewis representability theorem, which is true in this setting. So yeah, I stop.
Thank you. Questions?
So in the first theorem, should I think of the right-hand side as the infinity categorical notion of Bet module?
Mm-hmm.
Since Bet module is kind of like a classical way to present split square zero extensions.
Yeah, yeah. So in the algebraic setting, the same theorem is true, and this is the way we actually define square zero extension for infinity rings.
But I mean, that's like a way that you can define them for like
For whatever.
for basic algebras or
Yeah,
any
sure.
kind of
I mean that's
products.
yeah. That's Quillen. Quillen remark says that. I mean Quillen remarked once that abelian roots in commutative rings over A is a commutative ring, is a module.
Right.
This is just the infinity categorical transformation of this.
Is there any reasonable finiteness condition that you can impose on an analytic space, derived analytic space to get a perfect cotangent complex?
Yeah, I mean, it's always almost perfect.
Well, but
Yeah.
can you make it perfect?
Yeah, because all the morphism are of finite presentation. Because I'm only considering finite dimensional complex analytic spaces. So like this is saying that the cotangent complex is always almost perfect.
No, almost perfect I understand, but it can still
Yeah.
have infinitely many homologies. And it will, by your property, fall, right? If you
Yeah.
take a non-local complete intersection and analytify, you'll get something with infinitely many homologies. So coherent cohomologies, but maybe infinitely many.
I should have said that from this property it follows that we have the same connectivity estimates of the cotangent complex in the analytic setting as we have in the algorithm. But that's another thing.
Right, but this is all about analytification. The question is, if you start with something analytic, which is not the analytification of anything algebraic, can you still put
Yeah.
can you still put a finiteness condition so that you get something perfect?
Well, but I think it's always true because like in the algebraic setting, the fact that the analytic cotangent complex is perfect if the morphism is from schemes of finite type every time. Because so in the algebraic setting, let me do for the absolute cotangent complex. So you have X a derived analytic complex analytic, let's say. Then to show that the cotangent complex of this guy is perfect, I can reason locally on X. So I can assume that up to restricting to some open subset, there exists a closed immersion in the analytic affine space, which is the analytification of the affine space. Now I have a transitivity SIP, so here I leave over the point. So I have a transitivity sequence, which is now analytically. Now this guy here, it's perfect because the analytification. This is just the analytification of the cotangent complex of this guy, which is perfect. On the other side, this is a closed immersion, so this I can compute it in an algebraic way.
Yeah.
But the structure sheaf of X is of finite presentation because it's a quotient on the structure sheaf of this guy. So the analytic cotangent complex will be perfect because a map of derived rings is of finite presentation in the homotopical sense, if and only if the truncation is of finite presentation and the cotangent complex is perfect.
I don't get that. So you know, forget about analytic. Let's just start with a scheme.
Yeah.
Which is embedded in an affine space given by polynomial equations, and it's not a local complete intersection. Then the cotangent complex is not perfect. And it is locally finite presentation as a scheme, but not locally finite presentation as a derived scheme.
Yeah.
So
the same thing happens. Yeah.
Okay, so
finite condition, what do you mean? You would like something like quasi-smoothness.
Quasi-smoothness or something like locally finite presentation for the derived structure.
Oh yeah, okay. So yeah, I didn't prove anything like that, but when I was in Harvard, Jacob explained me that he's able to do something like that.
So there is some kind of definition of
which is the same. Like there is a category of analytic rings And just I say that an object here is of finite presentation if the map in analytic rings from A like commutes with the field coefficient.
I see.
Okay, and it's
Okay.
like A is of finite presentation if the analytical tangent complex of A is.
Okay, and then you can run the Michel and Bertrand's argument to say that these guys are free algebras with a ladder of the differential,
Yeah.
but maybe on infinitely many variables.
Yeah. So it's the same thing.
Okay. Okay.
Yeah.
Any more questions? Thank Mauro again. So I remind you that we have